Now, I'd like to welcome Adrian James up, and we're going to go right back in time, a few thousand years. Adrian James is founder and director at Adrian James Acoustics, and Adrian is one of the authors of BB93. You've been heavily involved with advice to the government over the years, the acoustic standards in England, and also you're a co-author of the Essex study. And your work has, again, been tireless on many, many things. So Adrian's going to tell us about larger lecture theatres, but you're going back thousands of years to Epidaurus and then compare that to the modern day. So thank you very much, Adrian.
Yeah. Thanks very much indeed, Colin. Yes, thank you indeed to everyone at Echophon for inviting me here again, in spite of my last paper, which I seem to remember involved a roll of acoustic gaffer tape. And of course the famous catnip acronym, and also for inviting me to talk about something which is not school acoustics. After 20 years of only presenting papers on school acoustics, you have no idea what a relief it is to be able to talk about something else. So there's a bit of history to how this all happened. Every textbook on acoustics mentions Epidaurus and ancient Greek theatres and tells us how great the acoustics are. But of course, all we experience when we turn up there is the acoustics standing in the empty theatre without an audience. In fact, we stand on the stage and drop a coin or talk, and we can hear the sound coming back at us. Now, as a theatre designer, I can also tell you, if I stand on the stage of a theatre and I drop a coin and I hear an echo coming back from the theatre, I get really worried. So, this is not good theatre acoustics. So my colleagues and I had an idea about perhaps it would be a good idea to take some measurements and create a computer model to show the acoustics as it would have been in the original theatre, which is a very, very different building, and also with an audience in place. It's very difficult to take measurements with an audience in place at the theatre because it accommodates about 17,000 people, and that's a lot of people to bus in for 10 minutes of acoustic measurements. Now, I mentioned to Shane Cryer that I was going on a holiday, a sailing holiday in the area, including sailing up and down the Corinth Canal, which was very interesting indeed, and incidentally is a lot narrower than it looks in that picture. It's also a lot shallower. And Shane said, well, while you're there, I'm sure one of my colleagues at Echophon in Greece can organise access to the theatre at Epidaurus. Indeed, I will come and help you to take the measurements. The man is absolutely selfless. He will go to any trouble at all to enjoy a nice sunny holiday, to come and help to take some acoustic measurements. So here we are. This is known as a large theatre because actually they've got a small one at Epidaurus as well. They have a spare. Let's just think a little bit about how these theatres evolved. This was built between 300 and 400 BC, so getting on for 2,500 years ago. The Greeks did not have a great deal of structural technology, so they couldn't build anything like a modern theatre. They couldn't even build something like the Roman Colosseum because they didn't have the concrete for it. The Romans basically invented the best concrete that's ever been built. So what you're thinking about in a theatre, you have a stage, you've got actors, you want to get as many of your audience as possible close to the actors, they've all got to be able to see the actors. How else can you do it than by having a circular raised system like this? There is no other way of doing it. And what I am going to say at the end of this is very disappointing, which is that actually the acoustics that come from this are exactly that. They are the acoustics that come from the form of the building. There were not little green men coming down to tell Aristotle, this is how you build a theatre for great acoustics, because it doesn't actually have great acoustics. Please don't tell the Greek tourist board that I'm giving this talk, because they allowed me into the theatre to take the measurements, and it's very bad news. But this is still how we design open-air theatres. What people do, of course, is they stand on the sweet spot and the very centre of the circular part of the stage, which is called the orchestra, just where Shane is standing there. and they talk and they hear the sound coming back at them and say, wonderful acoustics. Except, of course, that there's normally 500 other people in there. The coach tour has just turned up. They're all talking, and you can't hear what's going on anyway. This is about 7 o'clock in the morning. It was actually quite cold. It had just finished raining. We were standing there looking slightly bemused, wondering how on earth we're going to get all these acoustic measurements taken in the 45 minutes before the first coach party gets allowed in. And fortunately, the theatre dog turned up to help us, so that was all okay. Incidentally, the stage is largely kind of dust and sand. Of course, when the theatre was in use, or when it's in use for modern concerts, they put a timber floor down. We think probably it originally had a stone or marble floor, but it's possible that it was timber. Anyway, it would originally have been much more acoustically reflective than it is now. And that turns out to be important. So we used a sound field microphone for taking these measurements, and I don't think this has been done before. The idea was to be able to determine not just when the reflections were coming back to us, but also from which direction each individual reflection comes. And again, that turns out to be very important, because what we're going to do is to try to eliminate the effect of any reflections which would not have happened in the original building when there were 17,000 ancient Greeks in it. So, sound field microphone on the right there. 4 channels. You probably all used these things before. They're very good value. They're cheaper than your average B&K omnidirectional microphone. You can actually calibrate them, but we weren't looking at absolute levels, so who cares? And you can also put it on a tripod and persuade some helpful person like Shane to generate very carefully calibrated impulsive sources by blowing up a balloon and bursting it. Big red balloons always work best, because for some reason they were very reluctant about allowing us around with firearms or any kind of explosive device to create impulsive sound. We thought about using WinMLS or another kind of swept sine signal, but actually it just required more equipment than pragmatically I could bring with me on a sailing holiday. I was pushing my luck with my family by doing this anyway. Yeah, this is a holiday. So we measured reverberation time. Why would you measure reverberation time in an open plan space like this? Well, very simply, so that we had something to compare with previous measurements by other people. Very good paper by Garda and Galakis, which measured basically everything a few years ago. We just wanted to check that we were getting it right, we were in the right ballpark. So, yep, okay, there's the reverberation time. We don't care actually what it is, as long as it agrees with what Garda measured. Worth noticing that, of course, as you get down to lower frequencies, there's a lot more scatter in the results. That shouldn't surprise us at all, because it always happens. It's a function of signal-to-noise ratio. So this is a stupid question. Of course, RT is not the right thing to measure for an amphitheatre. What we're really interested in, fundamentally, is the impulse response here. Unlike an enclosed auditorium, the reflected energy that reaches anywhere in the auditorium is very much lower than the direct sound. The direct sound is really, really what's going to be important when we have a full audience in here. So what should we look at? Strength, G, clarity, center time. Center time is very interesting. I like center time. We measured it very carefully. It varied a bit with location, but the results were generally less than 20 milliseconds, which again is an indication of a lot of early energy and not a great deal else. Directional analysis of the reflections. This was why we were using a sound field microphone. Nearly all the reflected sound reaching anywhere in the auditorium within 50 milliseconds. And I'm talking about from the stage to the audience now, not actually within the stage, because actually we don't care too much about that. Most of the early reflections are coming off the stage floor. When you have a hard stage floor, 2,500 years ago, when they had a stone floor or a timber floor in there, you would get a lot of very useful reflections off that, and that's still a basis for the design of open-air theatres today. The lateral reflections coming off the tiers, that band of blue around there, all of those individual reflections coming back to someone in the audience of those tiers. Remember, we're in 3D, so the sound is going to come from the stage, bounce off one of those tiers, and actually most of it is just going to carry on going straight up. Nobody's going to hear that again, the birds maybe. All of that stuff is going to disappear when the audience is there, because ancient Greeks were fairly absorbent. They had legs which got in the way of the tears and so on. There's a very interesting paper written about the acoustic effect of that very carefully shaped tiers. Actually, the tiers were very carefully shaped that way because it's the only way that people could walk around the theatre without falling down. What's written about the shape of them acoustically is absolutely correct, but in practice, they would have had legs in front of them, which kind of spoils the effect. We also got very strong 85 millisecond reflections off the Skena wall. Now, the Skena is the building that would have been behind the theatre, and it's basically your backstage area. It's 2 stories high. We know that. There's a lot of archaeology done into the location and the height of it. So we recreated all of this in an acoustic model. I won't tell you what acoustic model we used, because if I do, then the person who wrote it will send me an angry email about it. We do have a license for it. It's just that he doesn't like us doing anything. So we put in the absorption and scattering. Hey, there's only one material in here, really. It's stone. It's not even stone in a great condition. We know that it's going to be fairly scattering. We know it's not going to be hugely absorbent. And by adjusting those absorption and scattering coefficients, we end up with something which matches our measured reverberation time in the existing building. Brilliant. Then we create the acoustic model and we tidy everything up. We make the stone a lot smoother. That's easy to do in a computer. And we start looking at results. We've put the Skena in at the back in the next model here. And you see that was quite a substantial building. Again, a lot of scattering, a lot of reflection. This is exactly what you want, actually, in a modern auditorium. You want any sound that goes back to be reflected forward. Of course, in a modern auditorium, we would also have some kind of orchestra shell overhead to reflect sound back down, and we don't have that here. So we relied on the archaeologists to tell us roughly what this should look like. There's also some very good papers written about it, and also there are still some surviving theatres which have the Skena buildings to look at. Quick comparison, again, T30 reverberation time against with and without the audience and with and without the Skena. Really, the big results are, of course, the reverberation time decreases quite sharply when you get the audience in at high frequencies. Low frequencies, well, basically reverberation times in a big space like this at 125 hertz. I would hate to say that those results were actually really valid. The presence of the Skena slightly increases the reverberation time at low frequency, but hey, it's an open plan building. It's an open ceiling building. The RT probably doesn't tell us much anyway. So let's have a look at G, loudness or acoustic efficiency. Well, of course, that introduces more useful reflections into the sound which reaches the audience, so it increases the gain. Some of those reflections might be late reflections rather than early ones. We'll have a look at that. Putting the audience in, of course, they're a bit more absorbent, so that reduces the G compared to the empty condition. Also, basically, we still have no surprising results yet. Now, let's look at clarity. And during this work, I had a bit of a thought about clarity, which is, think about the definition of it, which is that it is effectively a ratio of the reflected sound which reaches us within 80 milliseconds of the direct sound, okay, compared with the total sound. So where did this 80 millisecond figure come from? Well, it was derived actually for smaller rooms, for small concert halls, maybe going up to about 1,500 people, not for something which seats 17,000 people. So let's be a little bit careful about what this clarity does. Of course, with an audience in, again, your nominal reverberation time is going down, so the fewer late reflections, better clarity. Is that a good thing? Well, I'm not sure that it is. If you look at this graph here, we have a series of very strong reflections which come off the back wall, off the Skena, just after 80 milliseconds. If I move back towards that wall, that reflection becomes earlier, and it drops into 75 milliseconds. If I move 10 meters forwards, I'm further away, and it becomes just over 80 milliseconds. Nothing is going to persuade me that that difference between 75 and 81 milliseconds is going to reduce the subjective clarity that much. The same applies to speech clarity, of course, 50 milliseconds. Where did that 50 millisecond figure come from? Well, actually, it was small rooms used for speech, lecture theatres. So overall, what we have is, frankly, lousy clarity C80 and D50 figures, but it's still known as having great speech intelligibility. Why is that? And it is true, of course, we did the subjective thing. Somebody stands down on the stage, somebody else goes right up the top. Right up the top, incidentally, the tiers at the back were added by the Romans about 500 years later, one of the earliest theatre refurbishments that we know about. Yes, you can hear somebody talking, provided it's really, really quiet. I can do that in the car park outside my office in really quiet conditions as well, over the same distance. You know, it's the signal-to-noise ratio. There's no magic about the entire thing. In the presence of high or even normal noise levels, actually, the speech intelligibility is pretty poor. So, what did we learn about this in 15 minutes? Well, the acoustics of ancient Greek theatres, I'm generalizing here from Epidaurus, but yeah, they're all basically the same concept and shape. It's just Epidaurus is one of the bigger ones. They're just a function of the form that was forced on the builders by the need to build a theatre, really. The reflections of circular risers, which give us all these weird and wonderful acoustic effects, are absolutely nothing to do with what the users of the theatre would originally have experienced, because it doesn't happen when there's an audience there. As an aside to all of this, I've just realized that C80 and D50 are only helpful parameters under circumstances when they are helpful parameters. In other words, let's not use them for something which they weren't really designed for. They weren't designed for dealing with very, very large, effectively open rooms. And I am considering starting a campaign for the return of center time, TS, which is basically just a parameter which tells us how far along the reverberation, 17 minutes, how about that? Which tells us how far along the reverberation time 50% of the sound has reached us. That's a really useful measure if we can measure it accurately, because it doesn't have this very sharp cutoff that D50 and C80 have. So I'm going to stop using them for very large auditoria. Thank you very much.